Okay, so up until now, we found the definite integral. There have been some limitations on what types of functions we can integrate using. All right. So what were those limitations? So far with definite integrals, we try to do a definite integral. We can only do specific types of functions. So what do those functions look like that we can do very specifically? They were on your test yesterday.
They have a certain shape.
Certain shape. What specifically though?
Yeah, it has to be straight, like there's no.
Right. So it has to be straight lines. Right. It has to be like we can make triangles or rectangles or what? Trapezoids, right? Or what's the other shape? What's the one curve that we've done? Semicircles, right? So all those things where we have area formulas for, no problem, right? But that's not very many functions, right? There's very few functions that are just straight lines or that are just semicircles. So we're going to look at another way to do the definition. So it says, consider finding the area under this curve, which is not a semicircle. It's not a straight line. It's just a curve. Notice the area under the curve would be the integral from 1 to 2 of this function. Now at this point, we can't find that exact area. We don't have the tools for it. So the best we can do is approximate the area. And we approximate that area by summing the areas of smaller rectangles. We're going to use a rectangular approximation to do this. Okay? So first step when we're doing a rectangular approximation is we divide the interval up into a certain number of rectangles. In this case, for right now, we're going to do 4 rectangles. Okay? So let's break it up into 4 equal intervals. So 1, 2, 3. So notice I go 1, 2, 3, 4 little intervals. Now, since we have from 1 to 2, we're breaking into 4. How wide is each one of these spaces? Maybe a fourth, right? So we have a fourth wide. So notice the difference between 2 and 1 is 1. So we've got a space of 1, and then we're dividing by 4. So each one is 1/4. Okay, so if this is 1, then this would be 1 plus 1/4, or 4/4 plus 1/4, which would be 5/4. And then we'd have 5/4 plus another fourth, which would give us 6/4, or 3/2. And then 6/4 plus another fourth gives us 7/4. And then 7/4 plus another fourth gives us 8/4, which is 2. It says, then create 4 small rectangles with their bases on the x-axis and their upper left corners on the curve. Right. So if I start at 1 and I draw a line up until I hit my curve, and then I bring a line straight across, that would be a rectangle whose upper left corner is on the curve. Right? I can do the same thing at 5/4. So I go straight up, there's a point on the curve, come straight across, and there's another rectangle whose upper left corner is on the curve. 3/2, go straight up, and then across. There's another rectangle whose upper left corner is on the curve, and then 7/4, go straight up, over, and there's another rectangle. Now notice we have 4 rectangles. Is this area of the, if we add the 4 rectangles, will that be the exact same as the actual full area underneath this curve from 1 to 2? Will it be more or less than the actual area? Okay, so there's some empty space here, so it looks like it'd be less, right? So we're going to write this approximation as a summation of these areas. And to do this, we're going to use sigma notation. So we're going to say the area is equal to sigma, which you should remember from last year in pre-calc. At the very beginning of the year, you guys did series and sequences, and you did summations, which was series, and we use sigma. It's a Greek letter, sigma. And then a notation here is we start at some value, call it I, and usually we let I be 1 or 0. So we start here, and then we iterate. That's the iterator, and we add 1, and we go through a series of adding everything, or a sequence, and add each member of the sequence to get a value. Now notice, for each of these rectangles, the area, remember for a rectangle, is base times height. Okay? Now the height of the rectangle is the function value at this x. So I'm going to add up f of x sub I. And all this means is I'll have my first x, then my second x, then my third x, until I run out of x's, basically. Times, so that's my height, times the base, which I'm going to call delta x. Okay, so f of x sub I is the height of our rectangle, and delta x is the base of the rectangle. Now, in terms of our problem here, notice that the first height was f of 1. We don't know the exact y value because we don't know what function this is. But this is f of 1 times a base of 1/4, the width of our interval, plus, remember sigma notation is just a way of saying add up a bunch of stuff. So we've got our first term plus, we'll go to our next x value, so that'd be f of 5/4 times the base, which is also 1/4, plus f of 3/2 times the base, which is 1/4, plus f of 7/4 times the base of 1/4. Now notice, that's my last rectangle. I don't have a rectangle that goes all the way up to 2. Okay, I just have these 4 rectangles. So these are the areas of each of these rectangles being added together. Now, they all have a 1/4 in common. So we can simplify this just a little bit. Instead of multiplying 1/4 every single time, we can just do that delta x, that 1/4, times the sum of all of the function values. Right, so times f of 1 plus f of 5/4 plus f of 3/2 plus f of 7/4. Now this sum has a name. It's called a Riemann sum, named after George Riemann, who was a mathematician. He was actually a geometer, did a lot of geometry stuff, mostly in multi-dimensional stuff, like 4, 5, 6, 7 dimensions back in the late 1800s, mid-1800s. But this is one of his early works, basically. Was working with calculus, and he came up with this, and they call it the Riemann sum. It's called the left Riemann sum because we start from the leftmost point. Okay, so our first rectangle is made up of our leftmost point. Notice we calculate the delta x. We kind of did it just because the base here was 1/4 each. And the way that we can do that for any given problem is we find the difference in our interval. So we n minus start and then divide by the number of rectangles that we're going to break it up into. Okay, so in this case, notice we're going from 1 to 2. So 2 minus 1 is 1, and then divide that by 4. And that gives us our delta x. Now in a left Riemann sum, if we have a left Riemann sum, it says it will produce an area that is less than the true area when the function is increasing. We just saw an example of that. If we have a function that's increasing like we just saw, and we do a left Riemann sum, there will always be those empty spaces, right? So it's not the actual area, it's less than the actual area. However, if we have a function that is decreasing, in other words, it's going downhill over the interval, and we do a left Riemann sum, then notice what happens. It's more than the actual area, right? It's an overestimate. Okay? And I'm just using some, it doesn't have to be 4 rectangles. We can do this to any number of rectangles. We could have 3 rectangles, or we could have 1,000,000 rectangles. So example 1 says, if the function on the previous page, where f of x equals x squared, compute the approximate area under the curve using the 4 subdivisions shown. So in other words, we do a left Riemann sum. And then is this an approximation less than or greater than the actual area? So we actually have already done the work required to do this. We've got the left Riemann sum right here in function notation, right? So what we can do, and what I recommend doing, is what you write on your paper and what you do in the calculator may be different in some cases. And this is one of those cases. Okay? What I recommend doing when you're doing a Riemann sum, because one of these will be on the AP exam, and I say that because there's been one like for the last 10 years on the free response section. There's always something where it requires you to do a Riemann sum. And so the way we set this up was to say, well, the integral from 1 to 2 of our function, in this case it was x squared, dx, is approximately, notice I use the squiggly equals, that's approximately. And then using our left Riemann sum, well, it's 1/4, because our delta x is 1/4, times all those function values. Now in this case, we have x squared, right? And so our first x was 1. So we have 1 squared plus. Our next x was 5/4. So we have 5/4 squared. Our next x was 3/2. So we have 3/2 squared. And our last x was 7/2. So we have 7/2 squared. Okay. Now, because this is a squared function, there's nothing weird about it. What we're about to do is going to seem like, what's the point? But imagine that this were not just x squared. Imagine it were 3x squared plus 17x minus 2, right? Then doing this would be not quite as straightforward. You just have 3 1 squared plus 17 1, right? So you might just leave it as f of 1, f of 2, 3/2, or f of 5/4, and so on. And on your calculator then, we bring up a calculator page. And remember, we can define functions in the calculator. We can actually say, you know what, let's call it f of x. So f of x, control, and remember your template button over here with the colon equals above it. And the yellow calculators will do this as well. So you don't have a calculator, get a yellow calculator. Any TI Inspire will let you define it. And even most calculators will let you define a function some way, even if it's not a TI. And so we want f of x to be x squared. Okay, so it's done. And so now we can just type in basically our Riemann sum. 1/4 times f of 1 plus f of 5/4 plus f of 3/2 plus f of 7/4. Okay? So this way you don't have to worry about accidentally missing a square on one of the functions. You don't have to worry about whenever, maybe you get a cube root or something. You don't have to worry about making a mistake. You have to type the function in once, and you just have to pay attention to the actual values you're plugging in. So it takes some of the error out of it. And so we get an answer. And again, at this point, you just want to double check that everything you typed in is what you wanted to type in, because it's really easy to make a mistake typing in this calculator. Right? And so we get 63/32, or as a decimal by pressing Control Enter, we get 1.96875. So 63/32. Or 1.96875. And either answer is okay. Now, for this class, unless I purposely make the numbers like really easy, then you'll be allowed to, I'll let you use a calculator. Okay? Because on the AP exam, if it's not a non-calculator part, the biggest fraction to be working with will usually be like 1/2 or 3/2. They won't usually put something super complicated. So it's not that. Even this, I would wager that most of you could do this without the calculator if you absolutely had to. If there's a life or death situation, you could probably do it. But it's not really an issue. Okay. Next, it says subdivide the interval between 1 and 2 into 4 equal sections. So same idea, 4 equal sections. So 1, 2, 3. All right, so I'm trying to make them equal. Okay, so now it says create 4 rectangles with their bases on the x-axis and their upper right corners on the curve. So when I started on the left, I started at 1 and I went up, right? So what might be an easy way to go do the right? Yeah, let's start from 2. We start at 2, we go up to our function, and then we come straight across and finish off our rectangle. Then we go to, well, what were our x values? I guess we can fill those in while we're here. 1, 5/4, 3/2, 7/4. So we go to 7/4, go up to the function, straight across and down. 3/2 up to the function, straight across and then down. 5/4 up, over and down. So we're going to write this approximation as a summation. So the area, the total area will be the sum from I, and this again, in notation, it should be I equals 1 or 0, and it'll go to something. We're not too concerned with that notation just yet, but of f of x sub I delta x. So the same exact same as the left Riemann sum as far as writing this out. We'll see in a couple of days where it's different. But right now, exact same notation. So that's going to equal. Now we already went through the whole, we can factor out a 1/4, right? So these are all still going to have the same base of 1/4. And so we can leave that 1/4 outside. Now for our right Riemann sum, what is the first x value where we actually evaluate our function? In other words, what's our first height going from left to right? Going from left to right. So f of 1? Is that the height of this rectangle, f of 1? F of 1 is right there, right? Is that the height of the rectangle? No. F of 5/4 is the first height. Right, so we have f of 5/4 plus the next height, f of 3/2. The next height, f of 7/4. And then the last one we actually have f of 2. So notice how on a left Riemann sum we left out the final x value in our interval. On a right Riemann sum we leave out the first value in our interval, x value in our interval. Okay. And this again is known as a right Riemann sum because we can start from the right. Now for a right Riemann sum, if a function is increasing, like what we just saw, the function is going uphill, and we have a right Riemann sum, it will always give us an overestimate because we have all that overlapping part. Our rectangles are more than the actual area. However, if we have a decreasing function, and we do a right Riemann sum, I've flattened out too much. I don't want that horizontal. Do a right Riemann sum. Then notice we get a slight underestimate. There's that extra space. Okay. I say slight, that's not necessarily true. It's definitely an underestimate. So, same idea. Function on the previous, let's say this previous function was x squared. We want to compute the right Riemann sum. So the integral from 1 to 2 of x squared dx is approximately, so again, what we're really doing here is we are approximating the definite integral using areas of brace. Okay. And so we've got that 1/4 times. Now the first value we plugged in was not 1 this time, but 5/4. So we'll have 5/4 squared plus 3/2 squared plus 7/4 squared plus 2 squared. And so again, since we already defined our function, we don't have to do a whole lot here. We just have to type that in. We type in 1/4. We already have f of x defined, so we can just type in f of 5/4 plus f of 3/2 plus f of 7/4 plus f of 2. And so we get 87 over 32. Control enter gives us a decimal approximation, 2.71875. So 87 over 32 or 2.71875. Now, how does the right Riemann sum in this case compare with the left Riemann sum? Is it larger or smaller? Is it a whole lot larger? What was the left Riemann sum? 1.96. Is 2.7 a whole lot larger? No, there's not a huge difference, right? Not a huge difference. But since the left Riemann sum is 1.96, we know it's an underestimate, and the right Riemann sum is 2.71875. We know that's an overestimate. The actual definite integral has to be between those two values. We actually narrowed down the exact area under that curve from 1 to 2 to between 1.9 and 2.7, which is not too bad. We've narrowed down to a pretty small margin. So I wonder if we get more accurate. I wonder if we can get better. So let's see. So this time we're going to do 4 subintervals. we got 5/4, 3/2, and 7/2. And it says this time, create 4 rectangles with their bases on the x-axis and the midpoints of their top segments on the curve. So the midpoints of the top segment on the curve. So each rectangle has a top segment, right? Our goal here is that the midpoint of that is on the curve. Okay? So how the heck do we get the x value of the midpoint of that segment? So it's something between 1 and 5/4. So how do we get that? And how, right, but how do we get that exact x value? Divide what? Divide what by 2? So the distance between 1 and 5/4 we know is a fourth. So half of a fourth is an eighth. So you're saying that this x value is 1/8? So it'd be 1 plus 1/8, right? Okay. Can we generalize that? Is there a way that we can get a little bit more general where given any 2 endpoints, I can always get the middle of it? How do we do that? Like, okay, so let's say, so Corpus is mile marker 0. Okay, let's say San Antonio is mile marker 100. It's not, let's say it is. What's the midpoint between Corpus and San Antonio? Okay, 50, right? So let's say San Antonio is 100 and Austin is 200. What's the midpoint? 150? Yeah? Halfway between 100 and 200 be 150? Okay. So let's say we want the midpoint between mile marker 50 and mile marker 175. What is it? Divide what by 2? Okay, so we add them up and divide by 2. All right, so try that with the Corpus and San Antonio. 0 plus 100, 100. Divide that by 2, gives us 50. 100 plus 200, 300. Divide that by 2, we get 150. Okay, so the way we find the midpoint is we add up the 2 endpoints and divide it by 2. Okay, so we've got a rectangle with this midpoint on the curve. We've got a rectangle, and again, I'm going straight up from the middle right here on the curve. Straight up from the middle on the curve. Straight up from the middle on the curve. Okay. Now, what do you notice about this set of rectangles now? Is it going to be an overestimate or an underestimate? So it's got some over. Does it have any under? All right, so it has some over and some under. So it's like, well, don't know. It's going to be pretty darn close, though, now. We're actually filling in some of these gaps. Okay, so let's write the approximation. So again, sigma, or area, equals sigma, I equals 1, 2, and again, we'll usually have an upper bound here on here, and we'll get to that, but it's not with this. F of x sub I, delta x, and that's going to equal, now, are our rectangles any wider or narrower than they have been before? No, they're still 1/4 across, so we still have a base of 1/4. But now to get our height, we're going to find that mid x value. So f of, and our first x value was 1 plus 5/4 divided by 2. That's what gave us the 9/8. So 1 plus 5/4 divided by 2. Plus f of, so our next x value will be halfway between 5/4 and 3/2. So 5/4 plus 3/2 divided by 2. Plus f of, between 3/2 and 7/2, or 7, that should be 7/4. 3/2 plus 7/4 divided by 2. Plus f of 7/4 plus 2 divided by 2. And we call this the mid-Riemann sum, because we're using the midpoint. Okay. Now, for steadily increasing and decreasing functions, there isn't a specific, it's not necessarily an overestimate or an underestimate, but it's definitely between the left and right Riemann sums. Okay? Which means Remember, the left Riemann sum is always an under or an over estimate. The right is always an under or an over. So the mid is between them, just like the definite integral is. So this is going to be closer to the actual definite integral than the left or the right would be, except under very extreme situations. Like, yeah, I have to come up with something. Okay, so let's do the same idea, this time with a mid Riemann sum. So the integral from 1 to 2 of x squared dx is approximately 1/4. Now this time again, let's think about this for a second. When in doubt, you can use the calculator to do some of these fractions, get the what's going on. So we want 1 plus 5/4, which is 9/4. Right? Divide that in half, and we get 9/8, which is what we thought it was. So the first one would be 9/8 squared. Right? Plus our second one. Well, let's see. We want 5/4 plus 3/2. That's 11/4. We'll cut that in half. So we get 11/8. We want to guess what the next one's going to be without doing anything? Okay, so based on pattern 9, 11, we're going to guess 13. But rather than trusting our guess, because many times there's things that we think are right and they just don't work out, let's just double check. So we want 3/2 plus 7/4 divided by 2. And nope, we get 13/8. And so what will the last one be? What should it be? 15/8. Right. If you think about it, it would be 1/8 before 2, so 16/8 minus 1/8 would be 15/8. And again, we don't have to actually do the square part because we still have f of x defined. Right? If I didn't have it defined, I would define it. But so we've got 1/4 times f of 9/8 plus f of 11/8 plus f of 13/8 plus f of 15/8. And so we get 149 over 64, which is 2.32813. It's actually 0.8125. But so 149 over 64. For 2.328124. 2.328124. Now, how does this value compare with the left and right sums? So look back at the values we got. So the left Riemann sum was 1.96. Okay. And then the right Riemann sum. Okay. So how does this relate? Is it right in the middle of them? Yeah. Well, let's check. Okay, so recall the left Riemann sum was 1.96875. So 1.96875 plus the right Riemann sum. Okay. Okay, that's 4.6875. Divide that by 2. So is it right in the middle? No. Okay. And I only bring that up because there are cases where it will be right in the middle. Okay. But that's not a general rule. So you can't assume because you may have a problem where that happens, where the mid actually ends up being the average of the left and the right. I've had students who then make the assumption that it'll always work that way. Notice I'm being very clear. It doesn't always work that way. This is an example where it doesn't. And so if you're asked for the left, the right, and the mid, you can't just find the left, right, and then average those to get the mid. It doesn't work that way. Okay? Questions or concerns on left, right, or mid Riemann sums? Okay. So, yeah, all we're doing here is now because we can't get the exact definite integral, we can't get the exact area under this curve just yet, we're able to approximate it using rectangles. So we're actually evaluating, we're approximating this integral now. Okay? So whenever you start working on the assignment, take a look at the instructions really quick on the assignment part. Now at the very top, these instructions are for the entire thing. For each problem, sketch the function and the subdividing rectangle. So every single one of these, you'll have a sketch of the function and the appropriate rectangles. Okay? Then you're going to follow the directions. It'll say a left, a right, or a mid-Riemann sum, and it will say how many subdivisions. So it's not always 4 rectangles. You need to read the directions to determine that. Okay? And then answer the last question, is the area excessive or deficient relative to the true area? So excessive would be greater than, and deficient would be less than. Okay? There's only 7 of these problems because, I mean, they're not super time consuming, but they take a little bit longer than just 2 plus 2.